do we get rid of this? There we go. All right, so you've seen this problem before, and in fact, with more complicated things there than just x squared, but I want to illustrate something to you. Most of you now, from what I've done on the exam, know how to do this. You take, let's suppose I wanted to find the slope at x equals -1. I go through this process. You can either estimate it by taking 2 points on the curve and actually putting a line through. That's the common sense way to get an idea of what the slope is going to be. Or you could take, you know, the a and then let the a slide to x1, that business. So if I do this for x1 equals -1 and I go through the process, most of you should be comfortable now with this process. You get to a point a equals you get a -1 and then you let a slide to -1 because that's what you want to evaluate the slope at. And then you'll get an equation of a line, y is equal to -2x -1. This should be pretty quick at this point because we've been doing it again and again. The reason this is complicated is if I was mean, I could give you 10 problems on a test and just give you one function and tell you to find it again at a different point. You have to go through all the work again. So for example, if I had to look at x equals 3 for the same function above, I'd have to go through the whole process again. I would take x1 equals 3, y1 equals 9, x2 equals a, y2 is a squared, plug it all in and go through the process. Do you see any familiarities with what I did for x equals -1 with x equals 3? Like if you had to compare the two with each other, are you doing some of the same things? What do you mean by same things when you're comparing one with the other? When you're canceling, and right before you cancel, what are you doing before you cancel? Factoring. What formula are you using to factor? Difference of squares. It's the same formula even every time that I'm using. So even though I had to do the procedure again, it feels kind of the same. Oh, it's difference of squares. When you're doing your work at your, at WebAssign, you might feel that too. Oh, here's difference of squares showing up again. It's the same kind of process. And then if I asked you that same question of x equals 5, let's suppose I gave you 3 problems on the test and they were all these 3. Would you be happy? Well, because you know how to do it, but it would be irritating, right? What's the point of that? What am I trying to assess? I'm giving you busy work at some point. So it's busy work. And so most mathematicians say, most mathematicians can cuss pretty good. So they say, no way I'm going to do that again. I'm not doing that. That's how most mathematicians just stay back and say, I'm not going to do that again. I've done that already once. It's kind of mindless. It's boring. And so what they say at some point is, I'm doing the same things. Why don't I, instead of letting x1 be a number, let x1 be something that I can put into a box and then go through the process and automate that process so that I can stick the number in at the end and it gives me a formula and I'll have to do the work over and over and over. So if I do that, suppose x1 was a box and I can fill in the number into the box. Then I would go through the process. X1's a box. How do I get the y1? Whatever is in the box, I square it because it was f of x equals x squared. You follow me? Okay, just check it. All right, so then plug them into the slope formula. Well, I got y2 minus y1 over x2 minus x1. Whatever's in the box would just follow through. And then the next thing I did, like you pointed out, I was just doing difference of squares every time. So I just factor that thing with the box in it with difference of squares. They slash out. The whole process now is automated. And I get an answer at the end, a plus box. So that means whatever I do, I can put the number into the box and it'll work. So then I let a slide to whatever's in the box. And I'll get whatever's in the box added twice, which would give me 2 times the box. So I don't have to do the work again. I just have to now plug numbers into the box. So if I gave you those 3 problems, you wouldn't do it 3 times. You just plug whatever number I gave you into that box, and it would give you the slope. Does everybody follow me? So this experiment with boxes, if you think about algebra, some of the difficulties of algebra is having an x, and what does x mean? Apparently, our minds can't think about algebra until a critical point and age. So I had a bunch of 4th graders that were studying for the Math Olympiads. And some of those problems in the Math Olympiads you can just knock out with algebra. So I showed them with x's, and they just didn't understand what I was doing. So then I used a box. You can put any number into the box. And then they could understand what I was doing. So something about the human mind, you can't think like that until around, I think, 6th or 7th grade. There's actually people who study when you can actually learn how to understand algebra and understand that you can put other numbers in there and what a variable is. It's a really highly complex way of thinking. 200 years ago, 500 years ago, not all people were learning algebra. Can you imagine that? Those were the good old days, huh? So if you want to put an x in the box to get it to look like an algebra formula, so put x's, and then you have two x's added together, the slope formula for x squared at any point is 2x. I have now a formula for this one function. So then I don't have to do it again. Cross out and cancel and all that stuff. So here's how we write it. We write f prime is equal to 2x. That just means slope. The slope function of f of x is 2x. So how do we test? In medicine, I have to test everything because no one believes me. I say something and they don't believe me, so I have to show them with data that it works. So let's test it. I already did the work for x equals -1 by working out all the details. The answer I got was slope is equal to -2. What if I take that formula, 2x, and I plug in x equals -1 into it? I get -2. Validates, so it worked. What if I try it at x equals 3? That's the second thing I got. I got m equals 6. Plug in x equals 3 into here. I get m equals 6. Can't see it because I have to scroll over. I get 6. They match. So my formula validates for the points that I already did the long work on. Is that an easier way to use 2x instead of x squared? Is that, you know, I've taught at many different places. I taught at Georgia Tech and I taught at West Point. And those are students who are very good with procedures. They'll come in for them, they'll say, if you start showing them the first way with the sliding, they'll say, oh, my teacher Fred in high school, he taught me an easier way. You just go 2x. Is that really an easier way? It's exactly the same way. What are they telling me when they say that? They didn't get it. They didn't get the whole point of what we're doing. They just understand the procedure alone. That's it. So they told me a lot of information in that comment. And in fact, in our second section at 1 o'clock, we had a student who went to got help from a friend who was in math at NJIT. And the guy said, I'll show you an easier way. And he came back and he said, I don't know why you're doing this. There's an easier way. It's not an easier way. Someone automated the process for you. It's still the same way. They just made it into a formula. So what they did, I did all the work for x squared. So let's suppose someone's really lazy and said, I don't want to do, what if I have x cubed? Then I have to go through this all over again. And what if I have x to the 5th? I have to do everything all over again. Mathematician thinks, I just want to do it once for anything with a power. Because polynomials are like the second thing that you work on. First work on lines, then you work on polynomials. So I would like to get all polynomials down. And so I'm not going to show you that. It's in your book, very expensive, large book, if you want to look at the proof. But what they did is they went through special functions and said, I have a formula for anything that looks like this. The slope will look like this. See, when n is 2, it's 2x to the 1. It's exactly 2x. So it validates on what I just showed you for x squared. For the natural log, the slope is 1 over x. If you're taking physical chemistry, is anyone taking physical chemistry in here? You should. It's a good class. If you can do that, you can do anything else because you need physics really well, you need math known really well, and you also need chemistry known really well. So only the toughest survive that. This is the only function, e to the x, that is the same slope as itself. That's really weird. This e is named for a mathematician by the name of Euler. Starts with an e, actually. Sounds like it starts with an O, but it starts with an e. And so it's named after him. One of the license plates when I was working at the Army, this guy would pull in and he had e to the x. I thought that was so cool. It is a cool function. It's the only one where the slope is exactly itself, and it shows up everywhere. Then we have cosines and sines. most people hate cosines and sines. Do you hate cosines and sines? Get used to it a little bit? Do we have to do tattooing of the unit circle again? It's just because we don't talk about them as much as we talk about x squared in math classes. So it's familiarity. You don't have as much familiarity with them. But these are special functions, and they show up. Circadian rhythms. People's circadian rhythms are periodic, and cosines and sines model that. We also see it with people's habits. People don't have the same habits every day, but on a long-term scale, they start to oscillate and get periodic, every Thursday I go out to eat with my friends, so my weight goes up. And then it comes back down the next day because Friday it's Lent, it's supposed to fast, it goes down. So we have these habits that are also periodic that you can follow with cosines and sines. They're also used, does anybody have a Fitbit or any one of those devices that you walk around with, accelerometers? They actually collect data at frequencies, and when you start plotting the data, they're periodic. You start seeing that. When someone's walking, it's a rhythmic motion. So that the best thing that they can model is walking because it's perfectly periodic. Something weird, like if you're a parent picking up toys and doing something like this, those kind of accelerometers don't do as well. They're called accelerometers. They're all the same technology, no matter what the price. So again, that's why these things are important. These special functions are important. So why do you have to know this? Most interesting things in medicine are special functions. They might be a nasty looking polynomial. They might be a log. I showed you a log in here before. And we see something called S-curves a lot. I'm going to show you something with S-curves today so you can see what that looks like. But they're more complicated. And would you have to know to take the derivative of it? My colleagues don't. But they know what it is, and they'll go and say, I think this is more complicated, and they'll find the right expertise. Or they might get a degree in it, like the guy that's applying for our job right now. So here's your homework, and I'm going to show you an example of how to do it. This is all going to be posted. I'll post the notes itself. I want you now to use the formulas that I gave you to find the slope. So not, the A business, because that's time consuming, and also you definitely have to go to Mathway to factor these things. They're not going to be easy because it's the fifth power. So I want you to find the tangent line for this particular polynomial. I want you to plot the tangent line in the original graph, curve on the same graph, and tell me whether it's correct or not. You'll know. I saw you guys, some of you had the wrong thing, you were scratching your heads, and you knew when you were looking at your Mathway graph that the thing was cutting in the wrong direction or something was wrong. So it's a way to triangulate and look. And then I'd like you to graph the original curve and the slope function. What should happen if you graph them both on the same curve, on the same graph? What should you see? Do you remember on the test I gave you on the last problem, I think it was maybe second to last or last problem, you had a function, and then I asked you to draw the slope curve? How did you draw that? That's B, right, correct. But what if you graph the slope curve, the actual slope, not the tangent line, on the same graph as the original curve? What should you see? I made you actually do that on the test. You had the original curve, and I made you draw the slope curve. Do you remember how you created that? The increasing decreasing graph. Wherever it's increasing, the slope curve should be above the x-axis. Wherever it's decreasing, the slope curve should be below the x-axis. And you can see that on Mathway. Graph them both and you should be able to see it. So do that. And do it for these other functions, 3 more functions. 2 more functions. So not 2 through 5. Yeah, 2 through 5. Do the same thing. It's not going to take you long. I really don't, because it's just a formula that's easy to use. So I'm going to show you how to do one so you can see it all the way through. And this is posted online, so on Canvas, and I'm also recording this.